Okay, everybody, we're going to get this session started if you're ready. Unfortunately, Matt Yost is stuck at home with COVID, so he asked Jim Ippolito here. I had it every other time. We've got Jim Ippolito here to take his place. He's going to give his presentation. Originally, he wasn't supposed to speak until tomorrow. Is that correct? So he's going to do the speak today and tomorrow. So if you were excited to hear it, you'll hear it now. If you have any questions, feel free to ask. And I'll just turn it over to Jim and let him get started.
Thanks. Well, obviously I'm not Matt Yost, so I feel like I've been through a tornado. I just flew from Denver to St. George, and I got off a plane, and somebody picked me up and brought me directly here, and here I am, all of a sudden speaking to you about soil health. So if you were expecting to hear Matt and you want to leave, you won't hurt my feelings. My students leave my class all the time, so it's not that big of a deal. My name's Jim Ippolito. I'm currently associate professor of soil quality, soil health, soil fertility at Colorado State University. And I've been working in the soil health arena for almost my whole career, for the last 31 years, before it was called soil health. It was called we called it environmental soil quality at Colorado State University. And so what I'm going to do is I'm going to give you sort of a perspective on some research that we've done over, well, like the last 30 or 40 years that focuses on soil health, and most of it is current and some of it's a little outdated, and I shortened that section up in this talk. And then I'm going to tell you about some of, I think, the really exciting soil health topics that we have going on in Colorado that likely will touch other places in the U.S., specifically the western U.S., like here in Utah. And I work closely with Matt Yost from Utah State and Grant Carden from Utah State on soil health in the western U.S., and I'll touch on that a little bit today. So I work all over the place. I work in irrigated ag, I work in dryland ag, I work in forest fire burned areas, mine land reclamation, pasture lands, grazing lands, and I'm the type of person that can't say no to a lot of things, so I just love my job. And so we're here to learn about soil health, and I don't know your background, so I'm going to share you my background on soil health, and this is the direction I go when I talk about soil health to groups across the country. And when I talk about soil health, sometimes I've seen people roll their eyes at me. Like 5 years ago, people would roll their eyes at me when I would talk about soil health. Oh, here we go, soil health. So I've gone down this rabbit hole, and I talk about human health. And so how do we determine health? And if you were to look at these three individuals, and this is the story I tell people when I talk about soil health. I focus on human health first. And I say, okay, well, do we ever quantify human health? We really never quantify human health, right? So here's an example. Here's three cartoons, three different people, and which person is the healthiest. And it really depends on where you're located and your situation in the world, right? So this is what I present to people in audiences. I say, okay, if I was somebody who tasked these three people to run a marathon, but before they actually entered a marathon, I want them to go to a doctor and get tested to see whether or not they're capable of actually running 26.2 miles. And so if they were to go to a doctor, what sort of physical, chemical, or biological tests would a doctor perform on these three individuals to quantify their health? And so if they're going to run a marathon, the doctor might put them on a treadmill attached to some sort of ventilator to determine VO2 max, right? That's a physical attribute. They'll probably pull a blood sample, and they'll do some kind of chemical analysis on the blood sample. And after talking with quite a few of my soil microbiology or microbiology colleagues, down the road, probably not too far in the distant future, somebody's going to start looking at your gut microbiome. And so that's biological. And so we do the same thing in soils. When we quantify soil health, we never quantify health directly. We quantify physical, chemical, and biological attributes of soil health, and we combine those into some sort of score. At least some of us do. So I'm going to ask you this question. When you see this picture, which soil is healthier, the one on the left or right? Right. Right. And why do you say right? Yep, richer in color, more aggregated. It looks like there's good tilth. You see in the background on the right, you could see actually the surface is covered, right? And you would be correct. The soil on the right has better soil health, although you didn't say soil health. You told me attributes that contribute to soil health. And the thing I like about this picture, and I show this often when I talk, is that this is the same soil next to each other in a field. The soil on the left has been treated essentially with conventional tillage for 10 years. And the soil on the right, I think it says strip till, zone tillage. Basically strip tillage for 10 years. So the soil on the right has been treated rather, good versus the soil on the left. The soil on the left is a brick. It has no structure. It's structureless or massive. The soil on the right, you could pull an implement through that. And this is what we do. When we quantify soil health, we look at those attributes that you threw back out at me. And so in the soil health program that's run across the country, including in Colorado, we measure physical, chemical, and biological health, or attributes of health. In terms of physical, we measure the density of the soil, we measure aggregates, like you mentioned. Chemical, we measure pH, salt concentrations, we measure nutrient concentrations or available nutrient concentrations. In biological, we measure all sorts of factors. It says here on the slide microbial status, but we look at microbial biomass itself. We look at potentially mineralizable nitrogen, how much nitrogen is present that can be slowly released over time due to microbial activity. We look at something called beta-glucosidase activity. It's the ability of microorganisms to degrade relatively easily degradable carbon materials in soils. And at the center of all this, and you've probably heard this time and time again, is soil organic matter. And I keep this separate for a reason, because soil organic matter actually influences the above three. And so I've got these great pictures from Dr. Ray Weil from the University of Maryland, talking about soil organic carbon or organic matter and the importance of organic matter in soils. So this is from a long-term experiment in Maryland. The soil on the left was under 25 years of continuous corn. The soil on the right was under 20 years of continuous sod, and then it was broken out and put into 5 years of continuous corn. And what Dr. Weil probably had an undergrad or graduate student pull the aggregates out of the soil and put them in these beakers, okay? Then what they did was they added water. And this is what happened. The soil on the left, 25 years of continuous corn, dispersed. You could see the aggregates, but poof, add a little bit of water, and they dispersed, versus the soil on the right. And the importance of this is due to carbon. The soil on the left has low organic matter or low organic carbon versus the soil on the right. And that's relative. So he gave me these numbers. The soil on the left has about 1% carbon, organic carbon. The soil on the right, 1.4. If you converted those to organic matter, 1.7 versus 2.4%. Where I'm from, in eastern Colorado, that's sort of maybe in the ballpark. Sometimes we're a little bit lower than that in eastern Colorado, but that's the ballpark that we tend to hit sometimes in the soils that I work with in eastern Colorado. And so this message here, to me, is really important. It doesn't take that much carbon to increase aggregate stability. And that means a lot in soils. And in fact, when you look at soils, we want our soils to be well aggregated, like that picture I showed you earlier between the good, quote, good and bad soil. And this is what we want in the top left. We want our soils to be well, hopefully you can see the aggregation in this person's hand. And then there's some cover on the soil. And we don't want what you see in the bottom right-hand corner, right? We don't want to see wind or water erosion losses. And this is sort of the premise behind what you're learning here over this conference, is how to improve soil health. And how do we do this? And so when we assess soil health, maybe you've seen this picture before, we assess physical, chemical, and biological. And in fact, the chemical portion in the program I run at CSU, we split that out into chemical and nutrients, but it's basically all chemical. And then the sweet spot, the target for soil health, is where they overlap. And I would also say at the center of that is organic carbon or organic matter. And so let me tell you how we score, if you haven't seen this before. So I'm a scientist, and so as a scientist, sorry, but scientists have to quantify everything. And so as a scientist, we quantify soil health by scoring soil health some way. And this is how we do this. I follow this approach, and a lot of people follow this approach. More is better, less is better, or somewhere in the middle is better. Okay? So here's an example of more is better. More is better is organic carbon. And so this is a graph of total organic carbon on the x-axis versus a unitless score on the y-axis from 0 to 10. The program I run at CSU uses 0 to 1. It really doesn't matter. 0 being worst, 1 being best. On this graph, 0 being worst, 10 being best. And then you see these different curves that correspond to different types of soils. And so you basically collect a soil, you match it up to a curve, and then you give it a unitless score. That's more is better for organic carbon. Less is better is bulk density. How dense is your soil? If it's really dense, like that brick that I showed you in a previous picture, it was massive, it had massive structure, that would be really dense. And that would mean that more is not better, more is worse. And so that's the function you see in the top right-hand corner. And then somewhere in the middle is better is available phosphorus. And you can imagine this, right? If available phosphorus is really low, plants are going to suffer, they're going to be deficient. And if available phosphorus is too great, you might have environmental consequences that you just simply don't want to have. You might have phosphorus run off into sensitive water bodies, for example. And so somewhere in the middle is better. And I'm not going to go through all the curves that we use in the program that I use at CSU, but they follow these approaches. More is better, less is better, or somewhere in the middle is better. And so this is what we do. We go out and we collect soil samples all over the place. Those are the indicators, okay? We take those values and plug them into curves that I just showed you on the previous slide to come up with a score. And then those scores are integrated to give you a score for physical, chemical, we use nutrient, biological, and then overall soil health. They're integrated. And at CSU, we use a range from 0 to 1, 0 being worst, 1 being the best. And I'm telling you this for a reason, because I'm going to show you some data that shows you scores from 0 to 1. So I'm going to tell you some research stories. That was the lead into the research that myself and my group have performed over, almost like the last 30 years, 31 years now. And this first research project focuses on the shift in irrigation production, or production agriculture under irrigated conditions. And this is some work that I started when I was with the USDA ARS in southern Idaho. And I was fortunate enough to work with a great group of individuals on this upper Snake Rock watershed. It's 210 or 220,000 acres, fully irrigated watershed in south central Idaho, near Twin Falls. Twin Falls is sort of in the center of this picture, kind of. And what we did across this area was to find producers that had both furrow and sprinkler irrigation, growing roughly the same cropping rotations under the same types of soils. And we wanted to compare soil health within these systems. So I want to show you some pictures. Google Earth is really awesome. If you haven't played with Google Earth, you should play with this sometime. So Google Earth has a timeline feature up on the top right. Yeah, it's really fun. And this is what I did with this picture and the next picture I'm going to show you. So this is a picture of part of the area where I used to work. And this is from 1984. When you see a picture like this, and is anybody in here under irrigated ag? No? Yeah, one? Okay, so if you're under irrigated ag, dominated by irrigated ag, and you see lots of squares, it probably tells you you're under flood or furrow irrigation. And that's true for this picture. It's a little fuzzy, but you see a lot of squares or rectangles. This area in 1984 was dominated by furrow irrigation. If you fast forward, you take that timeline on Google Earth and just push it to the right. Here is 2016, the same picture, drastic difference in 30 years. This is due to, among other practices, EQIP from NRCS, okay? About 50% of this area on this slide is under furrow, and 50 is under sprinkler, roughly. It's a dramatic shift. And we were wondering if that had an effect on soil health. And here's the story I want to tell you with this project. So if you zoom in and you look at fields under furrow or flood irrigation, and you knew something about flood irrigation, you could probably tell me which direction water was being pushed across these fields in this picture. Okay? And yeah, it kind of goes all over the place, and you would be right. But let me show you a better picture. So if you zoomed in and looked at a picture of a flood irrigated field in south central Idaho, the soils are silt loams, they're talcum powder, they're baby powder when they're dry, and they're highly erodible. The soil in this picture, or the irrigation in this picture, occurred from right to left. And this practice of irrigation, of flood irrigation, has occurred over 100 years in this area. And what you see on the right-hand side of this field is the B horizon, the subsoil. It's highly calcareous, it's light in color, and it's exposed. And the surface, the soil surface from the right has been eroded and moved either down to the left, to the bottom of the field, or actually eroded off this site altogether. And so you probably don't need to be a soil scientist or a rocket scientist to tell me which portion of this field has poor and which portion of this field has high, relatively high soil health, because your instincts would be correct. So we had this question: if you perform flood irrigation for 100 years in this area called the Magic Valley, and then all of a sudden you switched and you converted to sprinkler irrigation, what would happen? So the farmers that we worked with had converted a portion of their property from furrow to sprinkler irrigation within 5 to 8 years before we set foot and performed this study. And so this is what we did. Let me go back one slide. So what we did was, in a field much like this picture you see here, we took soil samples across the tops of the fields, and we took soil samples across the bottoms of the fields, under furrow or under sprinkler irrigation. Okay, when you convert to sprinkler irrigation, you still know where the tops of the fields are. All these fields have been graded over time, so you can see where the tops of the fields are. And if you can't, then you ask the producer. Well, it's really not that hard to figure out, because there's usually an irrigation ditch that's still present at the top of the field. So we sampled the tops and the bottoms of these fields under furrow or sprinkler irrigation. Again, the sprinkler irrigation had been put into place 5 to 8 years prior to us setting foot on this site. And so what did we find? So I told you you don't need to be a soil scientist to figure this out. And you don't need to be a soil scientist to figure this out. Under furrow irrigated fields, the soil chemical, biological, and nutrient status, or indices, were always greater in the field bottoms versus the field tops. When I show these kind of pictures to my students, like that picture of that field in the top right, I say to them, no duh. I really do. I say no duh. Because look at the bottom of the field. It's darker in color. It probably has more organic matter. It might have a little more clay content, and you would be right. And the list could go on and on. Probably greater microbial activity. And if you were to combine all of these indices together, overall, the soil health at the bottom of the field was always greater than the top. And now here's the kicker. So as a scientist, we quantify why. The bottoms of the fields always had greater clay content, organic carbon, or organic matter, greater potassium, lower bulk density, and something called beta-glucosidase activity. It's a measure of microorganism activity and how they can degrade easily degradable carbon sources or substances. So we could quantify this. And in fact, if we were to go out and look at fields across this entire valley, we would probably use those 5 indicators instead of measuring 12 or 13 indicators. We whittled it down to a subset. The interesting part is the soil health work that we did, and this was published in 2017. We went back in the literature, and there was a scientist, a research soil scientist at the location. In 1985, he published an article that said the field bottoms essentially always out-yielded the field tops. And so we connect the data that we have now to the data from, 30 years ago. Wow. 40 years ago? I'm not doing math today. This 95, 05, 50, 30-something years ago. So this is where it gets fun, okay? So These farmers converted their fields from furrow to sprinkler irrigation within 5 to 8 years prior to us stepping foot onto their properties. And what did we find? We found that the field tops and the bottoms were the same in terms of soil health. Everything was the same. There were no differences. And I'm going to give you a fluffy answer as to why. And this is a fluffy answer coming from scientists, that I really feel that soils have a memory. And if you can start treating them better and making them feel healthier, they become healthier. And that, sorry, that's a really fluffy statement, but I really believe it based on this data that we found over the last 10 years. Okay, so I'm going to switch gears here. I'm going to talk about a program that we run in Colorado. This has been going on for about 40 years. And the title is, Can We Use Soil Health Testing in Organically Amended Production Ag Settings? And in those settings is compared to inorganic fertilizers or no fertilizers. And so I'm going to tell you a brief story about a 40-year project at Colorado State University where we focus on land application of biosolids. But the concept would hold true most likely for manure. And we have two settings that we've been working on. The picture on the left is a true production ag setting. We have a dryland wheat fallow and a dryland wheat corn fallow rotation that's been going for over 20 years. The project itself has been running for 40 years. The picture on the right is land application of biosolids to grazing land north of Fort Collins, Colorado. And that site's been in place since 1991. And what we've done is we've taken a look at the benefits or detriments of land application of this organic material in soils with depth over time, under production ag or under grazing lands. And I'm going to keep this really simple. What do we find? So this list that you see here, this is almost a complete list of the indicators that we collect in these fields. And so for physical health, we collect bulk density and aggregate stability. We determine those. For chemical health, pH, extractable phosphorus and potassium. I'm missing something in here. I think salt concentrations. We look at microbial biomass carbon, organic nitrogen that can be released slowly over time. Again, beta-glucosidase activity and organic matter. And without me going into the nuts and bolts of what we found, I can tell you that over 20 or 30 years, we either see trends in the positive direction or correct direction, however you want to call it, or we see significant improvements in these indicators and in soil health in these systems over time. And it's really fun to work in these systems because we're like the pasture grazing land system. There's actual cows that are out there on site that are grazed year-round, well, almost year-round. And we're using the material to improve above-ground plant productivity that improves animal health, that actually improves soil health. Now, you don't quote me on the animal health part yet because we haven't done any animal health studies, but they certainly like grazing in the areas that have received biosolids versus areas that have not received biosolids. So let me go back to ag. And maybe this is, there's one person who's in irrigated ag, so this might be interesting for you. Hopefully it's interesting for everybody else. So we just finished a study over in Fruita, Colorado, not too far from here. And we looked at conventional versus minimum till under furrow irrigation, which is a challenge, especially minimum till and furrow irrigation. And within each one of those systems, we either graze the residue with cattle or sheep, we kept the residue in place, or we baled and we removed the residue. And so if you know something about those 5 principles of soil health that the NRCS promotes, one of them is introduction of animals or livestock, and that was part of this program. And the challenge with this program, and it's in this portion of the field that you see that looks like big blocks, not the small blocks. We performed this over a 3-year period of time under continuous corn, under flood or furrow irrigation. And we use this implement called the crimper, this picture on the right. And what this crimper does is it takes the residue that's remaining and it tosses it outside of the furrow that you're going to use for irrigating. Okay, so it tosses the residue or trash into every other furrow. And so here's some pictures of what that implement does. The picture on the left shows you right after we pass the crimper through the field, and you probably can see where we're going to irrigate, right? You see the furrows that are relatively clean, and then the trash or residues tossed into every opposite one. And this is done for a reason. So if you don't know anything about furrow irrigation, the idea is to push water down, right? The idea is to push water down the furrow to the other end of the field. And if you have residue in that furrow, water doesn't like going down. It goes everywhere but down. It goes sideways. And so this implement pushes the residue, but keeps it still in the field so it can degrade and add to organic carbon. And then here's a picture on the bottom right of the corn, right around the 4th of July, looking down the row where the residue is remaining. So it's sort of a neat implement, and it does work. And it helps keep residue in place. And so what did we find? In this project, this is what we found. And there's a lot of data here. So I'm going to walk you through this, because I like this data, all right? And I'm going to walk you through the table. So, this is weird. Can you see that mouse? Okay. So we pulled soil samples from 0 to 15 and 15 to 30 centimeter depths. And then on the top, we have the sober baled, grazed, or retained. We're on this side of the tables, conventional versus no-till, and then some statistics, okay? And then on the left-hand side, we have physical, chemical, nutrient, biological, and overall soil health. So what I'm going to do is I'm going to walk you through this relatively easily. We're going to focus on residue management first. And if you look at the 0 to 15 or 15 to 30 centimeter depths for those attributes of soil health, almost in every case there's no significant difference. But here's the kicker. If in the 0 to 15 centimeter depth you look at what occurs, there's actually an overall improvement in soil health in the 0 to 15 centimeter depth with either keeping the residue or grazing the residue, introduction of livestock. Right? And the way this works is physical, chemical, nutrient, and biological indices actually are additive into the overall soil health score. So even though you might not see something significant in those 4 fractions, they add together to be significant. And that should sort of make sense to you. And in fact, if you were to look at the data in this paper that was just published last year, it's due to water stable aggregates, lower electrical conductivity, lower salt concentrations, greater potassium concentrations, greater beta-glucosidase activity, microorganism activity, greater potentially mineralizable nitrogen, the amount of nitrogen that's present in an organic form that can be converted to inorganic form that the plants can use. And there's greater microbial biomass, or microbial biomass carbon, in the sober, grazed, and retained. So a simple implement can do this. And this was in a short period of time. We started this study, and this data I'm showing you is 3 years after we started this project. If you look at conventional tillage versus no-till, this is what we find in the 0 to 15 centimeter depth. If you look at these numbers and you compare those two columns, conventional versus no-till, more often than not, no-till has a benefit over conventional till. And in that top 15 centimeters, no-till tends to have lower electrical conductivity, greater beta-glucosidase activity, greater microbial biomass carbon, or overall microbial activity, and greater soil organic carbon. In only 3 years after we started this project. Here's the kicker. When you look at the subsoil, those two columns of data actually flip, and conventional tillage has greater soil health. And we think that this is due to simply stratification. We're starting to see material that's being left on the soil surface, it's being taken up from below and being redeposited due to residue management on the top or less disturbance. And we're starting to see stratification, and who knows what's going to happen if we continue this project. It's a 3-year project, and it's over, unfortunately. But I think the take-home message here is when you think about soil health, you should be thinking about the top portion of your soil, the soil that's most exposed to the elements, right? And so how do we improve that area? And I think this points us in the right direction for flood irrigation. How are we doing? Doing great. I'm going to switch gears again because I love my job and I can't say no to a lot of projects. And here's another project that we worked on at our research farm in Colorado State University. And this was a project dealing with management intensive grazing. So we took this pivot that you see here in this picture, and we took it out of production ag. It was under real production ag. I can't remember the rotation. It had corn and it had some small grains in it for 10 years prior to us stepping foot on this site. And we basically turned the plants under this pivot back into perennial grasses. There were several mixes in here, but overall this system was under perennial grasses. And then in the bottom left-hand corner over here, this is where we have our cattle herd down here. Our animal sciences department runs their cattle herd out of this bottom left-hand corner. And so what we did was we took this field, and you can see it in the picture. You see those polygons? The polygons in the field represent paddocks, and the whole field is outlined with electric fence. Each paddock is outlined with electric fence, and we use management-intensive grazing, meaning we move the herd from one paddock to the next, to the next, to the next, after about 50% of the above-ground plant biomass has been consumed. And so we had a grad student that loved working with animals, thank goodness, and she was out there all the time dropping an electric fence and putting up electric fence to move animals, like every 3 to 4 days during the summer. It was really busy. It was a busy project. And so this is what we did. These pictures illustrate this. So the picture in the top left-hand corner, the cows have just been moved into a paddock. The picture on the top right-hand corner, they're sort of grazing. You can tell it looks like it's been grazed a little bit. Certainly the picture in the bottom center, they're grazed, and that fence is either dropped or getting ready to be dropped. And they're going to move over to the next paddock, and then that fence will be raised back up. And this just continued all summer, all spring, summer, and into the fall. So here's this picture again, and this is what the field really looked like. Every white line that you see here was electric fence. And again, thank goodness we had somebody that just loved working with animals, and she loved soils as well, so it was a perfect match for her. But she was out there all the time. So this is what we did. The circles that you see in this picture are where we soil sampled. We soil sampled 0 to 5 and 5 to 15 centimeters. We sampled 1 and 2 years after we implemented this project. We're actually sampling this now, 5 or 6 years after we implemented the project, to see longer-term changes. I'm going to show you some short-term changes here in a minute. And the circles, we sample these areas for a reason. And you notice that there's no circles in the top left-hand corner. And that's because that area was blown out due to one of these crazy windstorms that we have in the western U.S. Right? You experience those here in Utah, where you see just the soil blowing away. Well, the soil blew from left to right, and it cut the plants at the base and killed them all. And so we were a year behind in that corner, so we didn't sample up there. So what did we find? So here's the data. We started this project in 2016. We sampled it in 2017 and 2018. It was a master's student project. And on the left-hand side, you see physical, chemical, nutrient, biological, and overall soil health. Then across the top, you see the 2 years. And then you see the depths, 0 to 5 and 5 to 15. And let me walk you through this. So what did we find? In terms of physical soil health, we actually saw a decrease in physical soil health. And maybe this is not surprising to you, but when you put hoof pressure on a parcel of land that hasn't seen hoof pressure in a long time, the bulk density is probably going to go down, and you would be correct. So bulk density was actually increasing over time. It was becoming more dense. And in fact, one of the things that we found, we had one of these crazy 500-year rain events at the site, and the cattle were out in certain paddocks, and they trampled it. Well, the plasticity index became great enough. The soil was it was saturated, and the bulk density increased to somewhere like 1.65 to 1.75 grams per cubic centimeter. It's high enough to be really hard, really compact. And so one of the concepts we had with this type of project, if somebody was ever going to do something like this in real life, is to have a sacrificial area to move those cattle to, if you could, so you wouldn't damage this area where they're grazing. If you look at chemical soil health, we saw changes between years and with depth. And what we find is that it was all based on electrical conductivity or salt concentrations. Salt concentrations decrease over time, but they actually increase as you go down in depth. And it's just simply salts moving down through the profile into the system. I don't know if that's going to change or not. Maybe you'll invite me back in a couple of years and I can share the next story with you. In terms of nutrient soil health, what we find is, again, differences between years and depths. And this was all driven due to phosphorus. And phosphorus was decreasing over time, and it was decreasing over depth. And there's a caveat to this story, and the story is when we started this project, that soil was relatively deficient in phosphorus, the plant-available phosphorus, so we added plant-available, we added Ortho-P to that system. And of course, it's forming all sorts of soil associations with probably calcium minerals, and it's decreasing over time, or it's being taken up into the plants and taken up in the animals and being deposited as organic phosphorus, and we just haven't seen the change yet. So hopefully we'll see a change, and that's the next story, the next time I come back to Utah again. In terms of biological soil health, we see differences between years, and in fact, if you look at the two columns for the 0 to 5 and 5 to 15, they always increase from 2017 to 2018. We hope that this trend still occurs in 2021 and 2022. And it's due to biological activity, specifically beta-glucosidase activity. So microorganisms can degrade more cellulosic materials. There's greater microbial biomass carbon, so a greater microbial pool, if you will. And there's greater potentially mineralizable nitrogen. That's nitrogen that's found in organic phases that can be released slowly over time due to mineralization from microorganisms. And we think that's due to animal inputs. And to be honest with you, when you look at this data and you dig back into literature, what these trends or these significant differences tell you is that they're early indicators for increases in organic carbon. Those three important pictures I showed you from Ray Weil at the beginning of this talk. And so we hope we're going in that direction. And then overall, the soil surface has greater soil health than the subsurface. And that's where we want to see it, right? We want to see the soil surface increase in terms of its, quote, health, so the soils stay in place and they're not eroded. And then they promote biological activity, which promotes physical activity, which promotes chemical activity, and nutrient cycling and turnover. Okay. So I'm going to switch gears now. I'm going to tell you about some new projects that we have going on in Colorado. So we have a relatively big project that's focused on the Northern Front Range that focuses on irrigation management, so furrow or sprinkler irrigation or the conversion, and infield BMPs, so we have fields that are outfitted with conventional till versus strip till versus no-till, and then we have edge-of-field water quality monitoring. So you can see one of the devices here that is actually built at CSU. And then we have locations that have grass buffer strips that butt up against the ag field that is between the ag field and the edge of the field water quality monitoring device. And so what we're doing is we're trying to pair a whole bunch of things together, right? So irrigation management, how does that affect water quality at the edge of the field? I could tell you all sorts of simple things. I'm not going to do that, okay? But then BMPs with producers' input and soil health. And I have no data to share with you. We started this last year. We have like 5 different locations that we do this on. I work on mine land reclamation projects. This is really fun. It's not ag, but the concept's basically the same. So there's 3 locations in Colorado. This location on the left-hand side is near Leadville. It's just south of Leadville, Colorado. And if you've been there, it's beautiful, right? You're at the base of these 14,000-foot peaks, and it's a horrible place to work because you just want to go mountain climbing instead of work. And so this field, in this picture on the left-hand side, the inset picture, you see that picture? It looks like there's snow on the ground. It might be hard to see. But that's not snow. That's salt. That's a metal salt. It's zinc sulfate. And this area, if you know anything about central Colorado mountains, this area was mined heavily for silver. Started out as gold, but then it was a silver boom. And what miners did was they'd take the ore, they'd crush it, they remove the precious metal, and they'd throw the waste rock over their shoulder into the upper reaches of the Arkansas River. And those tailings, they moved downstream and they were deposited on bends in the upper reaches of the Arkansas. And metal salts were basically leached out due to pyrite oxidation. that white in that picture in the inset is zinc sulfate salts with zinc concentrations between 30,000 and 60,000 parts per million. So there's a reason why plants don't grow there, because there's nothing that can grow in there. So that picture was taken in about 1985. In 1995, some people outside of Colorado came in and helped reclaim this area by adding 100 tons per acre of biosolids and 100 tons of lime. And they added lime to raise the pH. The pH of the original, quote, soil was about 3. And now it's about, yeah, I know, yikes. And now it's about 7. And so in 2019, the crew that I work with, we went out to this site and we sampled for soil health. And I can tell you that it looks good. That picture was taken in 2019. It looks a heck of a lot better than in 1985, right? But I can tell you that there are some really nasty areas in here, and the plants can tolerate them. Lead concentrations, plant available lead concentrations of like 500 parts per million, when it should be less than 1, right? In normal soils, probably less than a half a part per million. Cadmium concentrations that are probably 800 to 1,000 parts per million, and the plants can tolerate it. Above ground plant tissue is excessive. If you were to feed that to a horse or cattle, and it was exclusively fed to them, they would not be happy. And luckily that doesn't happen. This area isn't very large. It's only a few acres in size. So the moral of this story is that soil health is improving, but the metal concentrations, you're never going to get rid of the metals, to be honest with you. It's reclamation in situ, in place, and it's actually working. It's preventing those metals from moving off site, which is good. The other two pictures, the top, well, let me start in the bottom right-hand corner. This is in the Box Canyon near Telluride. Have you been to Telluride? Anybody been to Telluride? No, it's beautiful there. And if you're in downtown Telluride and you go east into the canyon, you'll see this area that looks like a monoculture? It is a monoculture. It's all smooth brome, and it's a cap on mine tailings. And the people that manage this site manage it as if it should be your front yard, with the same fertilizer applications and the same irrigation methods every year without changing anything across this landscape. And it's the size of like 20 football fields. It's hard to tell in this picture. And so embedded within this area are areas that we've been studying, CSU has been studying since about 1992 or 93, where we've added different mixtures of different types of rocks and topsoil and different types of plant species. And so we're monitoring soil health across this this monoculture. And the same thing's happening in that top right-hand corner. That top right-hand corner is near Ouray, Colorado, and it's set up basically the same way. And I don't have any data to share with you from those two because it's sitting on my computer, and I haven't had a chance to actually dig into it yet. But I like playing in these areas because they're challenging. Heavy metals are they're just tough. Like you can't get rid of them unless you just excavate and put them someplace else, and then you have a problem someplace else. Y'all still with me? All right. Some new developments. I don't know how much you know about Colorado and soil health. Probably certainly know a lot about soil health in Utah, right? You've had a soil health bill in place in Utah for, no soil health bill. A couple months. Okay, so you're right with us. You're exactly where we are. So I've spent the last 2.5 years of my life eating and breathing soil health. I can't get away from it, and it's a good thing I like it. Actually, I love it, but I can't get away from it. And for the last 2.5 years, myself and about 200 other people worked on the Colorado Collaborative for Healthy Soils. Grassroots effort from the ground up. Producers, scientists, state officials, ranchers, oh my gosh, citizen scientists, you name it. There was 200 of us that worked on this Colorado Collaborative for Healthy Soils. It recently dissolved, and it's been taken up, I call it into the mothership, this Colorado Coalition to Enhance Working Lands. That's where we're housed now. But we're morphing that into something that I'll tell you about in a second. One of the things that this collaborative did was we pushed legislation through, just like here in Utah. We did this in 2021. It's a voluntary soil health program at the state level. So it's not being forced on anyone. If you want to join it, you can join it. If not, that's fine. But there's funding to back up the program that we run in Colorado at the state level and at the university level, and actually at the conservation district level and the producer level. And this was House Bill 1181 that just passed. It passed like in July 2021. So we're right where you are. Same, yep. So embedded in this program that we've worked on for 2.5 years is, among other things, a program called the STAR program. Have you heard of this? No? Okay, not too many people have heard of this. So this program started from a conservation district in south central Illinois, focused on improving water quality. And a few people in the big group of 200 that I work in knew about this program in Illinois, and we took it and we massaged it into submission to be used as a soil health program in the state of Colorado. And so this program stands for Saving Tomorrow's Agricultural Resources. And it's based on the 5 principles of soil health from NRCS, among other things. So soil armor, keeping your soil protected, minimizing disturbance if you can, plant diversity, continuous living plant roots if you can, and livestock integration. And this is how this works. At this website, you can go to this website and you can look at all the forms. There's 9 or 10 different forms based on the type of producer you are. Are you growing corn? Are you growing a small grain? Are you a rancher? You're raising cattle or raising sheep, or I don't think we have sheep in there, but definitely cattle. Colorado's cattle centric. Are you pasture land? We have 9 or 10 different forms that people can use. And a producer takes that form from this website, fills out the form with input from producers. We've created these forms. They're given a score from 1 to 5, okay? 1 being your average, and 5, you're doing all these 5 principles of soil health that are listed here near the top, okay? And so this is how we started this program. With funding from the state, we have conservation districts that are involved in this. I forget how many conservation districts we have. I want to say there's like 10 or 15 conservation districts across the state of Colorado. And within each of those conservation districts, we have 7 producers that are in the program. And everybody receives a little bit of funding to make sure that this is pushed forward. And then there's individual producers, and these spots I think are already filled. We gave out 100 free soil tests for soil health to the first 100 individuals that sign up for this program to fill out the STAR form. And this is what happens. So they fill out the form, like I said. They get a ranking from 1 to 5, 1 being you're about 80% of what everybody else is doing in your field. And by field, I mean like if you're corn producer, if that's your main crop. They get a placard that looks just like this score across the bottom of the screen, and it has a 1 to 5 star. And this is a project. I like to think of this as a project in sociology, and I don't do this type of work, but it's really a project in sociology to generate discussion between producers as to, okay, why did you have a 2 and I only have a 1? And they can look at the forms and start talking about what's different between farmer A and farmer B to hopefully nudge change in the right direction for soil health in the state of Colorado in a number of different agroecosystems. It's a monster, okay? And then embedded in the funding is what I'm going to share with you here. So we've used some of that money from the state of Colorado to leverage funds that we asked for through grants. And so we have a new 319 grant, so water quality grant. And we have 4 watersheds. The St. Vrain, that's up close to where I live, near Fort Collins. It's between Fort Collins and Boulder. The lower Arkansas, that's southeastern Colorado. The Uncompahgre, which is kind of southwestern Colorado, sort of. And then the upper Yampa, which is near Steamboat. And so we're going to go to these 4 areas this summer and work with 5 producers within each one of the watersheds to focus on what they consider BMPs or business as usual in the field, quantify soil health over the next 3 or 4 years, and then put in edge of field water quality devices on these fields. So they're all irrigated one way or the other, mostly flood irrigated. And then on top of all this, the producers have to fill out the STAR forms. So what we're going to do is we're going to start correlating all these pieces of the puzzle together. So BMP, soil health, edge of field water quality, and the STAR form. And can we start making sense of this data that we collect over the next several years? We're doing the same thing in a watershed called the Republican Watershed, something similar, I should say. This watershed is actually close to where you grew up. This is out in eastern Colorado. There's very little irrigation. And so we are tying in, I don't know why it says EQIP program, it shouldn't say EQIP. But we're tying in best management practices, soil health, and then in-field water dynamics. So we're going to be placing hundreds of these devices, these soil moisture sensing devices that are developed at CSU that cost like pennies on the dollar compared to what you could buy from Meter Group or someplace. And we're going to outfit these fields and look at BMP soil health and how that leads to improvements in water relations in soils. And on top of that's the STAR program. And then the last project, really close. The last project is a federal 319. So this is a water quality project. And we are looking at across the entire state of Colorado, about 100 producers with BMP, soil health, and infield water quality, and the STAR program embedded on top of that. And then there's one thing that's really exciting I want to tell you about this project and the last project I just mentioned. These infield water quality devices are developed by, his name's Jay Ham. He's a professor in my department, Soil and Crop Sciences at CSU. And he builds these that cost maybe $3 or $4. And the new prototype's going to cost a little bit more than that. But the new prototype, well, the old prototypes, you need to have cell service or you're taking a drive to download data off a card. We just gained access to the Argo satellite system. And if you don't know this system, this is the system that's used by scientists to track, among other animals, whales in the ocean. And I can tell you there's no wireless, there's no signal, right? There's no Verizon out in the middle of the ocean. And we're hoping to set up the first soil health network that taps into that system. And we don't want it to just be in Colorado. And so this is what's happening. And you may or may not know this, but we have a newly formed USDA soil health work group that's focused on land grant institutions. Almost every single land grant institution west of the Mississippi is involved in this, including Utah State and Colorado State. And it's entitled Implementing and Correlating Soil Health Management and Assessment in Western States. So what we're doing is we're taking hopefully the best and brightest of minds from land grant institutions like here in Utah, and we're coming together to try to solve problems that are the same or similar across our states. So we're not segregated, we're together. And we're doing this. We just started this actually in 2020. We have, in CSU, we have something called the Spur campus, and our soil testing lab is moving down to this campus. It's in Denver. It's near the Western Stock Show, if you've ever been there. And embedded in that, what we're trying to do is set up a regional soil health location that encompasses the states up and down the Rocky Mountain backbone, which is New Mexico, Utah, Colorado, Wyoming, Montana, and Idaho, and the land grants within those states. And every single land grant within those states, we all are together on this. And this will, if we pull this off with funding, this will be our home down in Denver, at least our hub. And that's that part of discussing this regional soil health center. And with that, that's my spiel. Do you have any questions? Thanks for your time. Yeah, that's a great question. The question is basically on this regional scale or Western size scale, how are we going to pull the data so it can be shared? Yeah. And so The concept that we've asked funding for is to first build out this center. And then after 3 or 4 years, when we start pulling data, to hire a database manager to put something together that's accessible by the public. And then it gets a little tricky, to be honest with you, because, there's privacy issues that we need to work through still. But we have people that in the Colorado Collaborative for Healthy Soils that have done this before. And so I'm going to turn this loose on an expert, to be honest with you, on that portion. But we want to create a place that you, like you, for example, can just go and look at the data, and you can do something with the data. And it'll be housed in one central location on some database in the cloud.
Is there, and I guess for privacy reasons, that it might be even more difficult to have it visualized spatially. That's a very easy way for people to understand that I understand why that would differ.
Yeah, that's a good comment. So the comment was basically having an easy way to visualize where the data was basically coming from. And so I'm sort of chuckling because about 3 or 4 days ago, one of my colleagues at CSU, who I work really closely with on soil health, said, "Hey Jim, did you see this website?" And I opened up the website, and it was a small soil health database, but it was a map of an area within the U.S. that had dots on it. And you could zoom in and you can go, "Oh, that's Bob's farm," and I don't know if we want to do that. It would be great to do that, but I don't know if we can pull that off. I work on another really large project that deals with big data across the U.S., and I work with a database manager that, I don't know how to put this, but they don't show maps, but they finagle data so you can't really tell where it's from, but you can if you knew behind the scenes how to correlate the jumbled mess up front that you see with the actual data back here. And I can't tell you how we're going to approach this yet, because it's like 3 years out. Yeah. But this is what we want. So I can tell you, this is a long story, but I'll keep it short. So our soil testing program at CSU, like Utah State has a soils lab. And we have it, right? Doesn't Utah State have a soils testing lab on campus? And I can't remember if Grant runs that or not, or doesn't matter. Anyway, we have the same thing at CSU. And they have a lot of data, and you know where it's located. Like, as a scientist, they have a lot of data that I want to mine, but it's in a filing cabinet. Like, they've been paper and pencil since like 1975 or something. They haven't converted. And so for me to go out and mine data, I don't have the time to do that. And from this point forward, when we work with our soil testing lab in Denver, they're going to dump their soil health data into this database. We're working closely with them to do that, because we can't do this anymore. We can't go through files. It's impossible to find anything. So we're going to have to work really closely with them, and we're going to have to work closely with our land grants to do this. But we're going to pull it off. And so we do have buy-in from the Western Regional Work Group. Every single person on that said, "Yeah, we'll do this. We'll figure out a way to do it." And then we have buy-in from the 6 states up and down the Rocky Mountain backbone. Any other questions? Questions from the virtual audience? No? Okay. Yeah, no.
I'm just very interested in how data can facilitate decision making. I'm probably also the least smart person in this room. So can you talk to me about, with your program, how do you see in the end game this facilitating conversations with producers to help drive decision making?
Yeah, that's a great question. So in the program that we run, well, I'll just talk about Colorado. In the program in Colorado that we are putting together and launching basically this year, to facilitate change, we know from day one that we're never forcing change on anyone, and that's, if you're in ag, that's just common sense. I've been in ag my whole career. And the premise behind nudging change, I'll call it nudging, is that we have producers side by side with us every step of the way. And we wouldn't do it any other way. And so to be honest with you, it's not going to be a geeky scientist like myself forcing change. It's going to be, I work closely with Roy Feltzgraff. He lives in Haxton, Colorado, or close to where you grew up. He is phenomenal in terms of the work he does in soil health, and he talks all the time about soil health, and he's involved heavily in soil health. And it's going to be the Roy Feltzgraffs and the Larry Lemkas and all these other producers that I work with in the ranching communities that are going to talk about this. I can't envision how this is really going to change, but that's the starting point, is the conversations with producers. And so I didn't share with you, but embedded in all these programs that are coming online this year are field days, with the hopes, if we get more funding, to have a program much like what you're having here today, but in Denver, and bring people together so we can talk about soil health and probably regionally, to be honest with you. So you should, like in 3 years' time or 4 years' time, you come to that conference, and then I'll be standing up here giving you my spiel, and then, hey, Jim, do you remember me? Oh, yeah, I remember that question. And we can have another conversation. In fact, there'll be producers at that conference that'll be talking as well. It's a cheesy answer, but that's the direction we're going.
No, that makes sense.
Yeah. Cool.
Okay.
Okay. All right. Okay. Well, track me down. I appreciate your time. Thank you.
Alright, so now we've got about an hour break. Welcome to stretch your legs and mingle. Do what you gotta do. I think they've got snacks around too. I'll hold to it. Don't come up again if they don't. But, yeah. Enjoy an hour session.
Thanks for getting me uploaded here.
Yeah, of course.
Yeah, I appreciate it.
Corey? Yes.
Okay, good. Yes. Troy hasn't gotten back to me yet, but if I track you down tomorrow.
Okay.
Hey, Corey.
Thanks for answering my questions.
Yeah, no, hey,
Appreciate it.
Keep it coming.
Yeah.